Hello again. We're looking some more at processes for counting complex arrangements of objects. In the first two videos, we learned how to count the number of subsets of a finite set, the number of bit strings of length n, and the number of k-element subsets of an n-element set. In the last video, we saw that counting these arrangements isn't always as simple as applying the additive or multiplicative principles, but that we have to beware of overcounting. In this video, we're going to take on yet another counting problem, counting the number of bit strings that have a certain weight. Specifically, we're going to look at the problem of counting the number of n-bit strings that have a weight of k, and we're going to introduce a new method for doing so, namely the extremely important idea of recursion and the related notion of a recurrence relation. By the weight of a bit string, we just mean the number of ones that are in that bit string. Or you can think of the weight as the sum of all the bits in a bit string. For example, here's an 8-bit string that has weight 4. Some notation here: bnk is the set of all n-bit strings with weight k. For example, here's the set of all 4-bit strings with weight 2. And you can see that the cardinality of this set is 6. So just to clarify, bnk without the absolute value signs is a set whose elements are all the n-bit strings of weight k. And this is the cardinality of that set, which is the number of bit strings of weight k. So let's think about the cardinality of B53. This is the number of 5-bit strings that have a weight of 3. One way to count this number would be by brute force. We just list all 2 to the 5th possible bit strings of any weight and then pick out the ones that have weight 3 and count those. That seems like a lot more work than necessary, and it wouldn't scale up if we were doing the same problem on much longer bit strings. So instead, we're going to introduce a powerful concept used throughout computer science to solve problems: recursion. Recursion is the process of solving a problem by reducing it to smaller or simpler copies of the same problem that eventually terminate in a starting condition. Recursion is used in many real applications, for example, sorting algorithms. One common algorithm, called merge sort, sorts a list of numbers by defining how to sort a 0 or 1 element list, then defining merge sort of an 8-element list as a combination of merge sort onto 4-element lists. Note here in the Python code for merge sort that the function calls itself on a smaller list. That's the very essence of recursion. Then merge sort on a 4-element list is done by calling merge sort on 2-element lists, which is then done by calling merge sort on 1-element lists. And then the starting conditions kick in, and the program tells how to piece together all these smaller lists. Let's see how recursion can be used to help us count the number of 5-bit strings of weight 3. First, here are a couple of examples. The key observation here is simple. Every 5-bit string of weight 3 has to start on the left with either a 0 or a 1. A 5-bit string of weight 3, therefore, is one of two things. It's either a 1 followed by a 4-bit string of weight 2. Since the total weight is 3, the rest of the bits would have to add up to 2, or it's a 0 followed by a 4-bit string of weight 3. Since no 5-bit string can have both a 1 and a 0 in the leftmost bit, the number of 5-bit strings of weight 3 will be the sum of two things: the number of 4-bit strings of weight 2 plus the number of 4-bit strings of weight 3. This is the additive principle, which we haven't seen in a while. We don't have to apply the principle of inclusion-exclusion here because these two sets have no elements in common. So, although we haven't yet counted the number of 5-bit strings of weight 3, we've expressed this number in terms of smaller and simpler versions of the same problem. The equation you see here isn't a formula where we can just plug in numbers and get an answer. It's called a recurrence relation. It expresses the quantity we want to find in terms of smaller versions of itself. Now we need to find out how to get these two other numbers. Well, we can make up a similar recurrence relation for B43 and for B42. Let's focus on B43. That's the set of 4-bit strings with weight 3. Now, just as with B53, every such string is one of two things. It must be either a 1 followed by a 3-bit string have weight 2, or a 0 followed by a 3-bit string of weight 3. Now we know there are B32 of the first kind and B33 of the second kind, and there's no bit string that belongs to both sets, so B43 is B33 plus B32. At this point, it's helpful to stop and make a generalization about BNK for any value of n and k. The same recurrence relation should hold. Let's say you have an n-bit string of weight k. Now that bit string has to start on the left with either a 0 or a 1. So it's going to be one of two things, a 1 followed by a bit string of 1 fewer bits, that is length n minus 1, that has a weight of k minus 1, since all of the bits have to add up to k. Or it could be a 0 followed by an n minus 1 bit string of weight k, since again, all the bits have to add up to k. The number of the first kind is bn minus 1 k minus 1, and the number of the second kind is bn minus 1 k. So we get this recurrence relation here for any nk by adding the two cardinalities together. We're going to use this recurrence relation to finally compute B53, but there's two special cases to bring up that will help us. One is where the n and k are equal to each other. The set BNN is the set of all n-bit strings that have weight n, but there's only one bit string in that set, namely the string of all ones. If you had any zeros in a string of length n, the weight would be less than n. Therefore, the number BNN is always going to be equal to 1. Similarly, BN0 is the set of all n-bit strings of weight 0. And again, there's only one thing in that set, namely the string of n zeros. So the number bn0 is also equal to 1. So, armed with the recurrence relation and these two special cases, we can now actually find the number of 5-bit strings with weight 3. We're going to do this with recursion and the recurrence relation we saw earlier, which I've copied here for reference. We'll also need the two special cases to help us out and the recursive process, that is bn0 and bnn both equal 1 for any natural number n. So starting with B53, we can use the recurrence relation to reduce this to B43 plus B42. Again, we don't know what those two numbers equal, but we can use the recurrence relation again on each of them to reduce some more. B43 becomes B33 plus B32, and B42 becomes B32 plus B31. Now I'm going to do a couple of things here. First of all, B33 equals 1, because that's one of our special cases. Second, I see two copies of B32, so I'm just going to combine those into one. I have B32 and B31, and again, I don't know the values of those, but I can keep applying the recurrence relation to simplify. B32 becomes B22 plus B21, and the B31 becomes B21 plus B20. Now, B22 equals 1. B21 is B11 plus B10. Here's another B21 that equals the same thing, and B20 is 1 because that's our other special case. Everything that remains is now a special case and equals 1. So we have 1 plus 2 times 1 plus 1 plus 1 plus 1 plus 1 plus 1. That's 1 plus 2 times 3 plus 3, which is equal to 10. So two observations to make at this point. First, this computation you just saw using recursion, it works, but it still seems inefficient. In fact, unless we write some code to do this for us, it seems like recursion is not a great way to actually count things. Instead, recursion is a really great way to identify the deep relationships between the objects that we are counting. So don't take this as a kind of algorithm. Think of it more as a way of understanding the mathematical relations between the objects that we're counting. And second, doesn't this seem familiar? The number of 5-bit strings of weight 3 is 10, and earlier we saw that the number of 3-element subsets of a 5-element set was also 10. Now, is this a coincidence? Stay tuned to find out.